formalization, as it were. So there will be a discussion about that. About half an hour, an hour, probably, I guess that will be here. Okay, so our next speaker is Ursula Martin. It's a pleasure.
It's a pleasure to throw litter at me, I know. Usually the students keep the paper darts until you got going, you know.
So Ursula has had a long and distinguished career, which I won't bore you with. So I'll just tell a joke instead. So, you know, it's an old saw that in the early days of our subject, computers were people who computed, not machines. Right? So I guess 100 years from now, provers will be machines that prove and not people. In which case, we will have lost the humanity in the act of proving, and that's kind of what Ursula is going to be talking about, I think.
Thank you. Thank you. So I'm starting with this because people who used to know me when I actually tried to drive theorem provers and totally and completely failed at doing some of the very smart things that are now being done, particularly with doing real number theorem proving and working with various companies on this. Over the past few years, I've somehow accidentally turned myself into the world expert on Ada Lovelace, and the only way I can sneak her in is with this wonderful slide. This is, I'm afraid you can't see the faint stuff necessarily in the front row, but this is a beer mat, or figuratively, an 1840s beer mat with Lovelace and Babbage talking about the bridges of Königsberg. And if you Google my name and Lovelace, you'll find lots more in the same vein. So I'm here to talk about something I've called the social machine of mathematics. Roughly, what I'm going to do is to be talking about a lot of ideas I've been having about, okay, we're getting pretty good at what the theorem proving community can do, what the big proof community can do. Now let's go out and find out what the mathematicians think about us, how they do stuff, and see if that can help us work with them more effectively. And I'm going to do that by talking about what I've learned from social scientists, math overflow, polymath, and some work on the impact of mathematics. But first of all, here we are. We've all come to Cambridge thanks to the generosity of the Isaac Newton Institute, the folks who've given us the money, or people's employers who've given them the money to come here to celebrate big proof. And even though my first few slides are just saying something that several people have said already, it's worth remembering that we've got a lot to celebrate. If you compare big proof now with what people were thinking about how people were thinking about it 20, 30 years ago, what have we got to be proud of? Well, big machine math proofs are feasible. There's Tom. Well, we've heard from Tom. So, tennis balls courtesy of the Varsity Tennis Club. So there you go. I mean, look at the respect he gets. They're professional engineering projects, and let's not forget that. Oh no, it's very easy to forget the amount of work, the amount of organization that goes into these projects. Some of the names on here are in the room, like Mark Adams, who was the project manager, who's somewhere. Hello, Mark. It's replicable. Well, did George replicate Tom, or did Tom replicate John? I'm not quite sure. But we have the Fight Thompson. It's definitely rewarded. There's Steve with a very expensive piece of chalk. And we know that we know it must be wonderful because Moshe Vardi told us so. If you're on Facebook and you're not following Moshe Vardi, he's so useful to keep you in touch with everything. Look, even Larry likes it, so it must be good. And all this activity, it's informing industry practice. People wonder, well, why is Facebook interested in this stuff? All that sort of social media stuff that we're not even kids anymore, Old people play with, but Facebook is a source of massive, big, chunky engineering problems. The reason I can load, we can all load Facebook on our devices is because a huge amount of work goes into getting it to work on all these devices. And this is Facebook London announcing their open source version of their software built by Peter O'Hearn and his mates, which is, and one of the things that they've picked up is how best to use the techniques in industry practice to run their stuff every night, bug checking. It's becoming respected and accepted in the math community. This is Tim Gower's blog, and Tim is, if you haven't met Tim, he's sitting at the back, and I think the community, hello Tim, Tim, a huge amount of gratitude for talking about what we're doing, making people aware of what we're doing. People, first sort of rule in lobbying, if they won't listen to you, find someone they will listen to. And Tim's blog has been very influential on all sorts of things. Here's Tim blogging. I'm sorry, I haven't put the date up on this, but this is Tim talking about a result using model checking to find a counterexample to a conjecture that various people have been working on. But the point is this remark at the bottom. I personally am relaxed about huge computer proofs like this. It's conceivable they made a mistake, but this is true of conventional proofs as well. This is a work by Konev and Lisitsa in Liverpool. So accepted in the math community. People are using them. This, I know some people were there. This is Dan Grayson. Of course, what's rather wonderful about this is it's actually a picture of a complete master of old school blackboard technique on the blackboards at the IHP in Paris, which are, huge old school blackboards. But here he is talking about his retirement project to formalize, it's to formalize half the papers he's ever published. Is that right? It's something like that. And there he is, explaining what he's up to, and a little bit up at the top is explaining the theorem provers that he's using. And senior mathematicians are advocating what we do. This is 5 very happy people because they've each run $3 million. The breakthrough prize is 2014. Donaldson, Kontsevich, Lurie, Tao, and Richard Taylor. Well, they won a prize. This is the Academy Awards. They've got a platform to talk about anything. And what do? They talk about us. Well, they talk about theorem proving. Here's Lurie saying, I'd like to see a computer-proof verification system with an improved interface that doesn't require 100 times time to write down the proof. Can we expect in 25 years? Tao is saying, can we verify every new paper by machine? And so on. So this is a great place to be. And the reason we're having this meeting, the reason Shankar has pulled us all together here, is to work out, roughly speaking, what do we do next? I pulled this wonderful picture off social media only yesterday, the map of mathematics, because I wanted to draw attention to the fact that here is this huge, wonderful world of mathematics stretching from the purest of pure mathematics over here to biomathematics, which has dropped off the edge, control theory, mathematical finance, and there are people in the room starting to use theorem proving techniques in several places in this picture, not just over here somewhere doing big pure math problems, but also in engineering, finance, and so on. So, how to understand what's going on here? Well, the way I started to think about understanding what was going on, actually when I got into this I was somewhat unwell for some time and I was stuck at home. And when you're stuck at home for some time, well, what do you do? Well, of course, you surf the web and find all sorts of things you never knew about before. And that's when I found out about polymath and math overflow and so on. But I started to think about, well, what do mathematicians do, and how can big proof help them? Well, how do you find out what mathematicians do? Well, as we all know, you don't start by reading the papers, because you turn to a random page of Andrew Wiles' proof of Fermat. Oh, in the Selma case, we make an analogous. Analogous to what exactly? And so on, and so on, and so on. More analogous. You have to know a heck of a lot. Well, you have to be pretty specialist to read it, and you have to be you know, part of the club to know what analogous means. So how do you find out what Andrew did to get there? Well, you could interrogate that pile of yellow pads, but that might not be about as illuminating as looking at, you know, all sorts of things. You could ask Andrew. Well, and of course people did. People asked Andrew for a TV program that you can find online, TV interview. And, well, this is TV, so they want the good story. They want the magic moment. They want the create. I guess a number of people have seen this, but so you know, they pause on this bit. Sometimes I realised nothing had been done before was any use. I had to find something completely new. It's a mystery where that comes from. And either he did stop with a rather dramatic pause, or they'd edited in a rather dramatic pause. I'm not quite sure which. But then, of course, he talks rather more about, yeah, what really happens. The other bit, the slog bit. Well, actually, he talks about that before. I tried patterns. I tried doing calculations. I tried to fit it in with some broader understanding. Sometimes I'd look at references. Sometimes I'd phone a friend. Sometimes I'd modify a bit, do a bit of calculation. So he talks about the slog. He talks about it a bit like an adventure game, a journey through a dark mansion. After 6 months or so, you find a light switch, so the breakthroughs, they're a culmination of, without the many months of stumbling around in the dark that precede them. Lovely phrase, stumbling around in the dark. G.H. Hardy, well, we're in Cambridge, we're in the city of G.H. Hardy. Some of you, I guess, are staying in Trinity, the College of G.H. Hardy. I guess it's a site of Trinity College, which G.H. Hardy's rooms were. Are you in them, Tim? No. Somebody must be in G.H. Hardy's rooms in Trinity. I don't know who it is. And here he is. I've edited this out of it. He's using the analogy, a sort of analogy of climbing. A mathematician gazes into distance range of mountains. It's simply to distinguish clearly and notify to others the peaks. There are some peaks he can distinguish easily, while others are less clear, and so on. When he sees a peak, he believes that it is there simply because he sees it. If he wishes somebody else to see it, he points to either directly or through the chain of summits. And actually, it's rather interesting language. You see, this is the 1920s. Hardy was a climber. He was friends with serious climbers like the Mallory and Irving, who were lost trying to climb Everest. This is very similar to the language that the last sight of Mallory and Irving was climbing through the mist, and it's very similar language. This whole metaphor of climbing is very powerful. Then he goes on to make this rather famous statement: there's such thing as proof. We can do nothing that point. Proofs are what little I call gas. Rhetorical flourishes to affect psychology. Well, if his metaphor was climbing and mountains and so on, Gilbert Ryle's metaphor is slogging through the jungle. Not how much practical experience of the jungle Gilbert Ryle had. However, the pioneering pathfinder has no tracks, don't follow them since there's nothing to follow. Well, he doesn't get there by sitting down and wringing his hands, walking over ground where tracks do not exist, where with luck, his issue and judgment, he might find them. It's a slightly different metaphor. It's a jungle. It's not a rather nicely elegant, nice clear mountain range. But then you get, well, we already had John Conway. I was taught by John Conway too. I think I didn't realise at the time. I knew he was pretty spectacular. I didn't quite realise he was a cross between Archimedes, Mick Jagger and Salvador Dali. Oh well. This is from The Guardian, which is a serious newspaper, folks. Yes. So it must be true. But John Conway talks about internalising this idea of space. John Conway is famous for studying these incredibly complicated combinatorial objects. I was thinking so geometrically, I used to imagine myself with lots and lots of arms and legs. I have 2 arms and legs, and I point them out, and they both lie in a plane. I'll use a leg as well, and blah, blah, blah. Now I'm trying to get to grips with 24 dimensions, so you seem to need quite a lot of arms and legs. I remember imagining myself stuck in this space with all my arms and legs in the air, trying to understand things, looking at stars, pretending they were lattice points and so on. And this is almost a sort of internalising the space. It's a kind of virtual reality computer game version. And if you've read Michael Harris's book, Mathematics Without Apologies, he uses the same thing to try and explain the mathematical process. Cedric Villani is another popular account of the mathematical landscape, and he's talking about the importance of using analogies between one landscape and another. Well, you can go on talking in this way for quite some time. Mathematicians talking, we've got a number of mathematicians who write rather articulately and beautifully. Do they really tell you what's going on? Well, if you talk to historians, if you talk to historians of science, they'll say, well, actually, no, this isn't really how you find out about how science works. You're looking at survivor bias. You're looking at some of the worst kinds of biographies. Somebody coined the wonderful phrase, the royal road to me, the kind of autobiography that does that. And all sorts of people get edited out, get left out, all sorts of factors get left out by these sort of great men reminiscing kinds of tale. But that's not to say we can't pick up something that might be important. So the 2014 Nobel Prize was won by O'Keefe, Moser and Moser, who essentially discovered, yes, we do have a GPS position in the brain. I simplify somewhat. But then you talk to cultural historians who will point out that although, because most of us live in it, this metaphor of knowledge as a landscape and exploring the landscape is just part of, we can't imagine a life without it. It is a thing. It wasn't there. It emerged with Romanticism at the beginning of the 19th century. It emerged a way as prioritizing certain kinds of knowledge, certain kinds of journey. Staying in St. John's, you have the Wordsworth room. Wordsworth studied at St. John's, very much associated with Romanticism. Or if you talk to social scientists, they'll point you to the work of Bourdieu, who thinks about social space and how we internalize social space to help us understand things. Okay, well, I'm going to stop the amateur historian bit for a bit. But how do we find out what's really going on? Well, what's really going on? Something's going on here. It seems to involve beer and tea and Coca-Cola and mathematics and hand-waving and Steve and Hugo are clearly onto something. And so to understand what's going on here, we turn more to the social sciences. Now, perhaps the social scientist who most got people starting to think about the practicalities of how science was created. The person one often associates this with is Bruno Latour. Latour and Woolgar laboratory life. They weren't studying mathematicians, they were studying biologists, bioscientists. If you're sending up what they do, then you say things, well, what they say is things like, I have to take a run at this because there are a lot of long words in it I don't often use. Mathematicians are embedded in heterogeneous assemblages that are imbricated in more extensive rhizomatic connections, themselves dependent on or even connected by diverse institutions that train, recruit, publicize, provide subsistence empowerment for the various mathematics actors that influence each other on these networks. Well, that's a lot of long words to say it's all a lot of complicated networks and people interacting to make stuff happen. I apologize to disciples of Latour for a travesty of what he says, but he's making a rather important point. And it's a point that becomes more important for our field when you start to think about all the big teams that are making things happen. All of Tom's team in Vietnam, they were doing something for this endeavor. And then you start thinking, yeah, these teams cost money. They have career structures, they have ideals, they need recognition, and so on and so forth. But the person who a number of you will have come across, indeed some of the people in the room actually in the book, will be Donald Mackenzie, who in 2001 published a book which is, he did the research rather earlier, but he was looking at, well, he called it mechanizing proof, but he was both looking at computer proof as those in the room would understand it, and also the use of computers in proof in other ways, like the original proof of the four-color theorem. And one of the points he makes is actually, however subtle you are with your machine, actually, it's up to us. We decide whether we're going to trust the machines or not. It's a contingent activity. There's another paper by Alma Steingart. She's analyzing the classification of finite simple groups. And she makes a rather interesting point that, yes, you value informality, but if you value it in too much, you can uninvent proofs. If everybody dies who forgets what analogous meant in Andrew Weil's paper, then you've kind of uninvented the proof. You've forgotten it again, because you've forgotten all the tricks of the trade, and that's particularly true with the classification of the finite simple groups that involves a heck of a lot of tricks of the trade. And if I just go back to this is kind of rather interesting, because way up there, sort of in the middle at the top, you can just see the word GitHub or VV. Oh, who's VV? Can't think. But Dan Grayson is kind of making that point, because he's saying, well, I use this bit of Agda, and I use this bit of that, and I use this thing for that. And he doesn't quite say, and if you run it again on a Tuesday afternoon with the following wind, it'll all work, but I can't guarantee it'll work in 2 years. But it's very much the saying, this is dependent on the systems I chose to do it in on the day. But of course, you want to look at one of the things. This is the only Iranian to win a Fields Medal so far, Miriam Merkazani. You want to look at some of the informal processes that are going on. You want to look at what people are doing, and that's where you start to talk to other people doing what Donald did, ethnographers, people who interview people, people who watch what's going on. Donald worked with somebody called Michael Barony, and they pointed out really the enormous amount of mathematicians' time that is spent, well, you might call it messing about, but it isn't messing about. It's decoding, translating, taking things, rephrasing them, reshaping them. And he makes this point with a crucial stage of disorder in between, and he points out that sometimes it's not just that the informality is awkward or a tiresome byproduct. It sort of has to happen. If you're going to start with one thing and change it into something that is actually a bit different, there probably is an informal, messy stage in between. You can't do it all by formal derivations. I've shown you Lovelace and Babbage. And Lorenzo Lane, who picked up his PhD just last week, is somewhere at that. Hello. He spent some time looking at exactly what people were doing, watching people standing around blackboards, and just identifying all the different things that they were doing when they were playing with ideas. Or indeed, all the different things that people were doing when they were hanging around in bars. The informal things you need to do. Why do you do it? Well, to help other people, or because you actually rather enjoy it, to gain rapport, to gain trust, to sort of populate your ideas, to put your ideas out there informally, so that when the guy gets your paper to referee, he doesn't completely diss it, to get a bit of shared understanding of what your fundamental concepts are, and so on, and so on. All the informal processes. And then if you start to lift these ideas and look at how they manifest themselves in other ways, this is a bit of work I did with Alison Pease, looking at math overflow. Well, I guess in this audience everyone's familiar with math overflow. It's on the Stack Exchange architecture. It's a question and answering system. It has all the things you've come to expect, like ratings and so on. What we did was we looked at a rather large sample of questions tagged with group theory. Why? For the utterly base reason that my PhD is in group theory, and I had some hope of understanding the flipping questions. But it's got all the things you know about upvotes and downvotes and so on and so forth. Here's a typical question, asked as it happens by William DeMeo, who's in the audience here. I chose it not because he's in the audience here, but it sort of fits onto a slide. But he's asking a question about, do there exist certain kinds of groups? And if that's a bit hard, well, can somebody suggest where I might look for a simpler example of the phenomenon? And the way in which Math Overflow works is people make various suggestions in a polite, sort of civilized way, and then somebody makes a suggestion that pretty much answers the question. That's somebody called Derek Holt, who some of the people in the room may know. He's a now retired group theorist from Warwick, who comes up and says, well, here's an example. He sort of, quickly types in an example, and then somebody else says, oh, by the way, I think you might have made a typo. Yeah, or, Q doesn't need to be odd. And Derek says, oh, yes, you're right. William says, hey, oh, that's pretty cool. I guess you could check it in. No, what do you say? Oh, I guess you probably can't easily verify it in GAP. GAP is the big computational algebra software for group theory. But then, of course, it raises a broader question. Even if you could verify it in GAP, maybe there are all sorts of reasons for taking part in this online coffee room. It's more enjoyable than verifying it in GAP. You put the world out there that it's quicker than verifying it in GAP. If you know in principle it can be verified in GAP, but you're thinking, oh, yeah, it's a bit like hard work, I don't quite know how to do it. And so we actually thought quite a bit about this. And we actually also went away and thought about looking at the kinds of questions that people ask. And this is related to the broader issue of what are people really doing. I've simplified the paper somewhat, but about a third of the questions are different kinds of conjectures. Is this true, or not necessarily expressed very forcibly as conjectures, but that's what they're essentially doing, conjecturing. A lot of the questions are the form we described as, what is this? Describe a phenomenon. Well, someone must have seen this thing, and somebody comes back and says, oh, yes, it's a rephrasing of that other thing. It's what Donald Mackenzie was saying. It's a sort of representing things in different ways. A lot of examples. Does anyone know an example, a counterexample? An awful lot of other, well, partly because I'm simplifying, but because this was group theory, various kinds of other that turned up quite a bit. Oh, can you prove this without using the classification of without using classification of finite simple groups? Or, Wikipedia says this, and such a textbook says that. Which is right? Well, you can guess which is right. But reasonable enough to ask the question if you're a beginner. Or they might be things like, well, this seems so obvious that surely someone's tried it. Why not? Why haven't they? Or what goes wrong? And of course, that's exactly the kind of question that lends itself to this informal format, and where somebody who knows a heck of a lot, very experienced, like Derek Holt, can come back and say, well, yeah, it doesn't work because various people tried it, blah. So it's pretty effective, or the community have found effective ways of using it, I guess that's what you say. About 90% of the questions we looked at were either resolved or moved forward in some way. The person learned something they haven't learned before. A lot of sharing of references or examples, the kind of thing that a mathematical knowledge management system might also be able to do for us. Not too much fuss about being precise. This isn't that kind of a thing. This is I'll ask a quick question in the coffee room and someone might have an idea kind of thing. A lot of the answers actually contain challenges or corrections. Of course, we didn't check which of the statements were actually true. This is just the and so when you start to reflect on this, there are various things you begin to realize. First of all, it's been really designed to work well, and there's sort of two levels of the design. There's all the features of the Stack Exchange architecture, the words the HCI community use are the attention economy. You've only got the coffee break to look at this thing. How's it going to lead you to the questions you might be the most rewarding user experience, shall we say. But also Senior members of the community put a lot of time into it. There's a meta thread, a lot of discussion about appropriate questions, appropriate behavior. What do you do if someone asks a homework question? What do you do if someone appears to be jumping into your student's PhD problem? And that's senior members of the community maintaining a polite, maintaining certain values they think are important and discussing that in a rather open way. We can all think of even online maths activities that aren't always like that. I'm not referring to you at all. The people who know the news group FOM, don't go there for a relaxing experience. So it's a really, it's quite an interesting, phenomenon from many points of view. Also, of course, that the things that are being picked up are very often things that aren't in journals, or even if they are in journals, they're not in a way you would ever find them. Particularly the examples. So the example, somebody will say that, well, there's this example in this paper, but what they mean is, well, kind of, at the end of a paragraph, somebody says, well, this might work for such and such a group, but it doesn't because, that would never be in the abstract. It would probably never be picked up by an indexing system. But it's just one person who read that paper. It's sort of stuck in their mind, perhaps because that group was one of their favorite babies. And every time they see a question, they see if it relates to that group. And if it does, they can tell the world about their favorite baby, the little group that nobody else understands. So that's polymath. That's Math Overflow. I now move on to, well, here I am talking about polymath, and there in the back row is one of the creators of polymath. Well, this is my take on polymath. Actually, if you want a lot of very interesting reflection on polymath, well, of course, read Tim's blog, read the other articles and blogs about polymath. But it's just a remarkable phenomenon. And it grew out of an idea of thinking about how people could collaborate to produce proof. It began on Tim Gower's blog. It began with a question about, it says on here, 27th of January 2009, gosh, getting on for 10 years ago now. Tim announced an experiment to attack an unsolved problem, a new proof of the density Hales-Jewett theorem. A lot of discussion about exactly how this would work, what the ground rules were, drawing the community in. And eventually the paper was produced with the author D.H.J. Polymath. And as part of the discussion of this, what emerged was, how were they going to do this? Well, they were going to do it on a blog with certain conventions, certain rules of good behavior, which were agreed on by the community. Be polite and destructive. Sorry, be polite and destructive. Boo! Constructive. Make your comments as easy to understand as possible. It's okay to be tentative, incomplete, or even correct. It's okay to make mistakes. Oh, there you go. Park technical details somewhere else. If you're going to take a bit of it offline for some time, then tell us. An ideal polymath research comment should represent a quantum of progress. I keep meaning to ask Tim, and now is probably not the moment, how much this is influenced by Hardy and Littlewood's rules for collaboration, which are share some of the same aspects of this. Perhaps I should just flick forward to remind you, for those who haven't seen it, what it looks like. So this is what it looks like, a conversation on a blog. So this particular one I've picked up here. Well, they're working on upper and lower bounds for something or other. Various people are commenting. Terry's maintaining a table, other people are commenting, and Terry's saying, well, I'm just going to put this up for now, and other people are commenting, and so on. That's how it works. But the polymath that achieved perhaps the most attention was Polymath 8. Polymath 8, they were trying to lower the bound on the twin primes conjecture. Well, Zhang had proved what you might call the that Zhang approved, there are infinitely many prime pairs bounded by, not by 2, but by 70 million. And Terry Tao and various others, over a period of very intense work, reduced the bound to 246. And you can follow it all online. It's really, really amazing. And here they are at work. One of the reasons I think this was quite amenable to this approach is basically you're trying to bound a big thing. So what you do, you break it up into chunks and bound each of the bits, and then hope that all the bounds add together to do what you want. So you can sort of share up the task. And Terry took on the role of the choreographer in this one. What are they doing here? Well, they've got to the stage where they're actually trying to do some numerical work. And they're sort of a bit concerned about the precision in maple. And so here they are. I don't know if you can read it, but that's the gist of this. Terry's saying, oh, I noticed the values looked a bit odd, but I trusted in maple without investigating it further, as you do. And then they're coming back to aspects of this. If someone would like to look over my Mathematica, it involves a mixture of stuff I borrowed from James, not you, James Davenport, but James Maynard in Oxford. But it's very straightforward, and Terry's saying, oh, well, looks as if we've knocked off that little bit of the problem. We could check it with any computational mathematics problems. And then Terry says, oh, I've checked it on maple. Well, so it must be right. Well, I wouldn't want to argue with Terry, but just because Mathematica and maple say roughly the same thing isn't always. Anyway. But that's the kind of thing. Of course, I can't tell you, no, I'm just giving a rather crass summary of it, but some of the things that we can reflect upon, looking at, I mean, the discussions, I should say, I was drawing attention to the perils of reading too much mathematical biography. The kind of discussions here, the kind of discussions on Tim's blog and Terry Tao's blog, very much the opposite. They're much more sensible reflection on what's going on rather than pontificating. But some of the issues that this raises, and they, after Polymath 8, the team published a paper themselves reflecting on the process, which is very, very, really worth reading. But it's worth looking perhaps at how, they reinforce certain values that they want the phenomenon to retain, values of being involving everybody, to the extent of having quite clumsy tools. So quite early on, various times people said, well, why did you use a blog? Why didn't you use something more sophisticated? And the answer is, well, we just wanted it to be very accessible. We wanted anybody, and I remember they're talking about people who live in maths departments who quite often have pretty under-resourced and not very good computing facilities. They're talking about people they wanted it to be accessible. And that trumped some of the other things you might say. Now, you can imagine some of us in the computer science community going away and designing something with lots of bells and whistles and nobody using it. But the fact that senior individuals in the field, senior mathematicians, took the time to take ownership of the thing and say, no, we're designing it for our community, we're taking ownership of it. And that made a huge difference. Reinforcing the values of being polite and constructive. But of course, they also reflected on, Polymath has not yet taken over the world. Now, some of the things that perhaps didn't meet what some of the hopes have been for it in the start. First of all, there may perhaps was some hope at the start that, people could just pick it up in the middle and make a contribution and then go away and do something else. But in fact, it turns out for dealing with these big problems, it needs a huge and intense commitment. And it needs somebody to choreograph it, as Tim has choreographed some, as Terry Tao has choreographed some, who not only has the technical skill and the authority in the community, but also the social skills, the people skills. And it's quite interesting to sometimes to look at some of the ones that have petered out. There was one, I'll be a bit vague, but very recently, deliberately, where somebody who wasn't Tim or Terry came along and said, right, I want to solve this. I'm going to need people to do this, that, and the other. And do you know what people said? People said, I simplify somewhat, but you could see what was going on between the lines. People said, well, why should I help you? So it takes, it takes a choreographer, it takes commitment. Certainly Terry Tower with the Trim Prime said himself, well, look, there are many things he could do with his time, and people were saying, why are these amazing mathematicians doing this when they could be doing so many other things? But also, it requires people to commit to the collective, if you like, in a way that is not necessarily part of mathematical culture. What will your 10-year committee say if your paper says DHJ polymath at the top instead of you? And it requires people to say, okay, well, I'm going to work on this as part of the group, rather than pursuing my own idea, which, it's a balance. Am I going to pursue my own idea, which might mean fame and reward for me, but maybe I'm not as clever as those guys. Am I going to join in with the community? But one of the other aspects that people talked about is you need to not mind making mistakes in public. And, well, there are people who don't want to do that because they haven't got tenure yet, or because they're just not that kind of person. And I think then it becomes a rather interesting question. Because if we're talking about values or virtues, and philosophers have a whole riff on mathematical virtues or mathematical values, then who said being comfortable with walking a tightrope in public was necessary to do advanced mathematics? You're sort of impose that the community, or a section of the community, is sort of prioritizing another virtue which is not necessarily, and when we talk about, a whole other thing about why certain groups individuals feel excluded from mathematics, well, that might exclude certain people. I know many people worry about the involvement of women, the involvement in mathematics, and so on. But it's an interesting point to discuss. But it is an amazing experiment, and I think it's an experiment that our community can learn a lot about, or indeed start to think about, well, how would we incorporate what we do with how they think? Don't worry about errors. That sort of thing. And perhaps one of the most interesting things about it, which, I was going to put that in my conclusion, but I better say it now, having launched on the sentence, is this idea of risk. And the idea that actually, because you're working with a gang of people, you can sort of take more risks. You can make a mistake and somebody else will catch it. You can say, oh, hang on, yeah, I knocked something up in Maple and it isn't quite working, but what the heck, it's probably right. But you can trust there'll be, in your gang, part of your community, there'll be a mathematical expert or a Maple expert who will kind of help you sort it out. So it's the fact that collaborating like this allows you to take more risks, because having a bigger community to catch you when you fall off the tightrope. But I did another piece of work on this, again in the spirit of the piece of work we did on Math Overflow, of looking at what you could learn in more detail about what was going on. You see, the kind of ethnography that involves hanging around in bars listening to mathematicians, well, good ethnographers are hard to find, and they can often, there are all kinds of things they can do, and hanging out in bars listening to mathematicians may not float their boat. But one of the things this does, of course, is it gives you an account of what's going on under the hood. Terry Tower calls it how the sausage is made, or the social scientists use the term backstage and front stage. what's going on backstage. And so we looked at a different problem, which you all, being very smart people, have solved by now, from one of the Math Olympiads, which was set up as a mini polymath problem. It didn't take days and days, and it didn't take months and months and months. It took 74 minutes for, oh, I've got it written down somewhere. No, I've got it written down. 147 comments in 74 minutes for people all over the web to sort out that one. Well, it's about points and lines and points and a line rotating, and it's called the windmill problem because it was the year the Math Olympiad was in the Netherlands. And after we'd looked at this, we discovered it was developed by somebody who a number of the Brits in the room might know, Jeff Smith, who runs the British, is a mathematician in Bath, who runs the British Olympiad effort. And here people are. Actually, on this, people spent a lot of time wondering about what it meant, a windmill. And there's a red herring, because it's described as, it's a line, sorry, can't see my pen. It's a line rotating in the plane and hitting points. But because of the way it's described, it's written as a windmill. You think of it as a half line, you think of the windmill's sails, and actually it's not true if it's a half line, it's not, it's a whole line. But that makes it quite interesting to look at, because a lot of people come to it and spend a lot of time puzzling over the fact it doesn't seem to be true for a half line. It isn't. But what Alison and I did was to look at, again, this is a simplified version just for the slide, but what sort of things were going on? Well, in these 174 comments, 147. Well, first of all, only 14% of them were proof steps. Obviously, at the end of the 147, they solved it. But what were all the rest? Well, 20% were conjectures. Well, the whole thing was conjectures, sub-conjectures, if you like. Developing intermediate concepts, examples and counterexamples, a particularly high proportion of those, because a lot of people came in and every time somebody new came in and was anxious about this half-line thing, you know, the same conversation happened again, really, because nobody quite had the energy to look back up the blog, I think. And a lot of other, and a lot of the stuff we ended up classifying as other was reactions to the, oh, it's not a half-line, oh, you know, just sort of social chat, which didn't fit into any of the previous categories. But, of course, again, this reiterated some of the things. Of course, one of the things you may well be thinking is Lakatos. Yeah, hey, Lakatos was right. Well, roughly Lakatos was right, but of course Lakatos is an artfully constructed artificial conversation. In Lakatos, people don't go down the same dead end twice. People don't actually have dead end, or if they do have a dead end, they learn something from the dead end. Whereas in this, no, people don't. You know, they just, something turns out to be a poor approach, and, well, it was a poor approach. There isn't the artificial, you know, Lakatos leaves all those bits out. But I know, other themes, you realise the importance of informality, the importance of error. It was the same ground rules as the big polymaths. But again, you know, that sort of raises questions. Well, how could our world help? Well, what are people looking at? Examples, counterexamples. You know, maybe you could sort of construct a formal proof on the fly alongside the informal proof. I don't know, there's many opportunities for, do we have a phrase yet? Mathematical knowledge managers? Well, I suppose if we've got knowledge management, we've got knowledge managers, but, you know, there's many opportunities for the broader activities. Now, the final piece of work we did, this will strike fear and dread into the hearts of people in the UK academic community, because it's about impact. Impact used to be just an ordinary English word until, perhaps I should just, so the UK, essentially we're an entirely state university system, and that means the state has to have a fair way of divvying up cash so that academics in Cambridge and Oxford get lots and lots of cash, and places in other, academics in other places maybe don't get so much cash. And they do this by having a beauty contest every few years. And in the last round of the beauty contest, every university department had to submit examples of the impact of their work. Well, this is one of the advantages of this from the point of view of actually going away and researching it is these were examples in standard format. Of course, they were they weren't complete works of fiction, but you know, some people are better at creative writing and advocacy than others. This is my former colleagues at Queen Mary University of London, title of case study, Informing Policy and Mitigating Risk. They're pros, you know, they are professionals at doing this. That's what the examiners wanted to hear. And this is a project all about analysing gas networks and electricity networks and looking for points of weakness and points of coupling. You know, when the gas goes down, lots more people use electricity, that sort of thing. So, because I got very fed up with bureaucrats saying, oh, mathematicians don't patent enough, mathematicians don't know they're born, if only mathematicians went out and got more patents, blah, 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 maths would be more useful. I went away and worked with a social scientist, you know, with a completely clear mind to do a piece of work. We analysed, we really did, we are very sad people. We analysed 209 of these things, and what we wanted to look at was how mathematics has impact. Well, to cut to the chase, you can find the paper in a journal called Research Evaluation. Who knew there was such a thing? Well, I didn't, till my co-author told me about it. One of the things, well, there are a variety of ways in which things can have impact. Instrumental is what the government is often looking for. You know, this thing was patented and the widgets were better. But sometimes it's a bit more complicated than that. There was a completely new insight, maybe coming from operations research, into how to reorganize the widget production line. So it was cheaper to make widgets. Well, that might be a conceptual impact, you know, the brilliant idea about reorganizing the widget construction line, etc., etc. But the importance for mathematics of long-term relationships, of keeping in touch with people, of developing a culture where working with people who are interested in applications was encouraged. There's a term called knowledge intermediaries. Knowledge intermediaries are the kind of people who just go around talking to people. And it's a role that, you know, many departments have that person who's good at going out and talking to companies, but they don't quite often recognize that they're fulfilling an important role. And also, of course, we realize that actually, as you might guess, just telling the story in a linear way, which is what the government wanted, is completely simplistic. This is a wonderful picture drawn by Jonathan Pitts, no relation, I presume, at Queen Mary. He's got a pretty good startup by now. I think he's probably your long-lost cousin. And he's a glutton for punishment in PowerPoint. But this just shows yellow is his government funding, green is his, oh, it's sort of faded to white, but white is his industry funding, all the very complex linkages that really led to the work. And I went to see the movie Hidden Figures. Has anyone seen it? Yeah, and it was rather amazing to see that it illustrated my paper. Isn't that nice of them to make a movie? And the plot, well, what's the plot of Hidden Figures? Well, they're trying to get those early American rockets off the ground in the 1950s. So Kevin Costner strides in. The first and possibly the last line, you'll hear this in a Hollywood movie, bring me an expert in analytic geometry. He doesn't say bring me a book. And so Kevin Costner playing Kevin Costner, Kirsten Dunst playing Kirsten Dunst, as she goes off and finds an expert who is Katherine Johnson was a real person. She turned up at the Oscars aged 100. And she's now why is, so you have your knowledge intermediary, why is Katherine Johnson there? It's because NASA had a long-term relationship with one of the historically black colleges in the area, had recruited talented women, including Katherine Johnson, who had a PhD in maths, to work as human computers, as Andy mentioned. Now, the problem the expert in analytic geometry is meant to be solving is, well, calculate the trajectory of the flipping rocket, okay? So her conceptual insight is that you don't do it analytically, you do it numerically. And the tech report is actually on the NASA website. You can go find it, which she says this. It doesn't cite much, you know, for people involved in UK ref politics, would it count? I don't know. Anyway, so there it is. So that's her conceptual insight. Building, capacity building, well, in fact, this is when the first computers are coming in, and then there's a whole team who get to work and learn to program and use it. That's a bit implausible. The new IBM machine comes in and that part of the movie. But, so there's the movie illustrating it, which was rather striking. Okay, well, we've got to get back to our world. I've been talking about how mathematics works, how mathematics has impact, how people collaborate. Of course, I haven't talked about the broader context. Another aspect of this UK politics is, well, it's awful stuck in the past. You know, what papers did you cite? Hey, who says mathematical publishing is going to stay the same? You know, and there are plenty of people talking about new models for mathematic publishing, new models for researcher productivity, new ways of accessing content, etc., etc., etc. Who says that in 50 years' time we're going to be stuck in the same model as papers in the Journal of the Royal Society? And this is my last slide. What do we draw from all this? Well, lessons for big proof. Well, first of all, the variety of opportunities, the varieties of mathematics. I had a rant at somebody in their talk, Larry, I think, for saying the mathematicians. Yeah. There are lots of different mathematicians, spreading from, you know, this lot in the middle, the pure mathematicians, over to pure mathematicians. Well, yes, it's about proving, building bodies of knowledge, proving difficult theorems, proving, you know, theorems that shed insight onto vast areas of the discipline. Right over here, well, what are people over here doing? Well, very often it's much more, it's not about theorems, it's about techniques, it's about applying techniques to practical problems, and so on and so on. There's a variety of opportunities for mathematics, not just proving theorems, but in mathematical knowledge management and all these other things. There's a variety of mathematical cultures and mathematical values, and you know, if that's the takeaway from things like Math Overflow and Polymath, it's finding a way of working that respects the mathematicians, that sits with the way that mathematicians like to work, and that means that they engage. There's the importance of things like, for the mathematical cultures that enable things to get out into the world, the importance of things like knowledge intermediaries, the importance of thinking about different ways that mathematics or indeed our stuff that can get out there. One of the interesting points, I think, is this issue of correctness versus risk. So we in verification often like to sell our stuff as, well, look, you know, it'll be correct. Use our stuff and you'll know it's correct. Actually, if you look at mathematics over the years, over the decades, correctness, for a long time, correctness didn't bother people all that much. You know, G.H. Hardy, if you read G.H. Hardy's papers, they're incredibly sloppy. Was it you, Tom, was talking about Hilbert, lots of mistakes in Hilbert's papers, but it was sort of, there's technical errors, and then there's also, well, writing sloppily was okay. You know, they're sort of two different aspects of it, aren't they? I heard, I'm afraid I can't remember who said this in the verification community, but it really hit home when they said, well, actually, we shouldn't try and sell theorem proving because of correctness. We could try and sell it as mitigating risk. look, you can take more risks, you can be more creative if you use a theorem prover and it's going to catch your errors. Does anyone remember who said this, or is this me imagining it?
Sounds like Rod Chapman.
Could be, yeah, don't know who. There's a whole issue of many kinds of mathematical knowledge, many ways of managing mathematical knowledge. Now I'm talking about lessons for big proof. Of course, one can also think about, will mathematics change? We were having an interesting side conversation last week about POPL, which is a conference that is starting to wants people to use a theorem prover. And various people said, well, hang on. Oh no, one said, this is great, but it's changing the culture. Is it changing the culture in a way we want it to change? Maybe we want our grad students to spend time in the pub talking about mathematics rather than being slaves to the theorem prover. Maybe actually, although using a theorem prover makes it very easy to write a paper about a system with 193 axioms, maybe we don't want to encourage people to write papers on systems with 100, the kind of culture changes that these things make. We want to think about these things. And we can think about even bigger questions. Will the way in which we think about mathematical knowledge change? This notion of a landscape of mathematics, big mountains that we climb. That's the way mathematical culture is now, has been since Hilbertish, but an awful lot of mathematical culture in the 19th century, the 18th, wasn't about that. It was about very different kinds of mathematics. Even the metaphor is it mountains that we're climbing, or is it a jungle that we're hacking through? But do we want do we want pure mathematics which we many of us love because it is the way it is, or it's got the whatever, another talk there. Do we want it to go the way of things over here, where you you do your little bit, but then actually you plug it all into a system, or pure maths turns, do we want it to change into a fully automated thing? These are other things, or will it do it whether or not we want it to? Well, I don't know. This seems a good place to stop, especially as I'm over time, with a cartoon that always seems relevant, but I don't quite know why.
Thank you very much.
Hi. Yeah.
So this windmill problem is very nice.
Yeah.
Has it been formalized? Do you know about this?
I don't know, but of course, half the problem is figuring out what it means, and then once you've formalized it, I don't know is the immediate answer to your question. Anyone at the back?
Ted.
Sorry,
Yeah.
a separate question.
Sure.
Yeah.
Not a comment on.
Yeah.
That was a lovely talk. Thank you very much.
Thank you.
And it has suggested all sorts of analogies, but there was your one of climbing mountains. And you can have a group of friends who go out climbing difficult mountains, and they share their skills, and they show each other how to get over this rocky ledge and this and that. As opposed to that, there are people who climb mountains in cable cars. And, going to the top of a mountain in a cable car is the end of mountaineering. And the question, therefore, is what is mountaineering, or what is mathematics?
Well, yes, I think that's one for another day somehow. But you see, one sort of touches on it by saying, what is it? A body of knowledge? Is it a body of techniques? Is it how is that knowledge accredited? I mean, that's how one would ask that question in the bigger, what distinguishes science from things that aren't science, and so on. But that's a whole degree course in the philosophy of mathematics, or the nature of science, or something. Everyone wants tea. Hello, Matteo. Yeah.
So, thank you very much. It was a very nice talk, especially pertinent for this community where we have a whole bunch of computer scientists working in automated reasoning and a whole bunch of mathematicians doing mathematical stuff. And I take your point that Lakatosh's book is a very sanitized view of a mathematical discovery process, if you like. But it's an interesting evidence also for what I think that a mathematician's proof is a social construct, which is that if a famous enough mathematician comes up with a proof then and convinces enough other famous people, then it will be considered to be a proof. And we have plenty of evidence that, and in the Lakatosh's book it's in form of Cauchy coming up with the proof of Euler's theorem, which was considered to be true for 50 years, and then oh my God, there were counter-examples, and there were monster-barring examples and all of that. And Cauchy then formalized the proof that would satisfy the computer scientist, and it's completely unintelligible, and it loses the intuition behind what the proof was about. Whereas for a computer scientist, I won't be able to publish a paper in Cade, for example, if I don't come up with a verified proof of my theorem, right? So how do we mitigate this difference between the two communities? Computer scientists would like mathematicians to use our tools. Mathematicians would like to, do away with all that boring stuff and let machine do it. But we don't manage to actually interact in the way that we share our tools with each other. So I guess your talk is in the realm of social mathematics. So how can we bridge this gap? I mean, I guess getting everybody in the same room talking to each other is one way.
Well, I think that is part of the thing. But I think you shift some of. I mean, this is a politician's answer, right? Because I don't know. You shift some of your, you shift some of your preconceptions. You start where they are, not where you are, and so on and so forth. You think in different ways, and we do have. But then sometimes you do it in ways that are not that are not things that we would think of as huge achievements. But, I mean, if you look at, we've got some of the talks coming up tomorrow. George's talk. A lot of the infrastructure work that we do is kind of aimed at that, and is important, or how you restructure things, how you present things. Sorry, that's not a very articulate answer. Shankar is leading us all to find an answer. Let's ask Shankar.
Oh, yeah, one more question.
Well, you get computers to drink beer with you.
Good. Yes, you get computers to drink beer. Very good.
I was missing an aspect of social part of mathematics, and that's how does one mathematician convince another one of the truth of the importance of what they are doing?
Oh.
I think this is a big piece of good communication.
I think that's the answer. Well, there's a long answer to that, and sometimes they don't. I mean, that's the answer. It can be one person convincing another person, or it can be, you convince a third person who'll convince them, or you convince it's the whole. But I don't think the answer to that question for mathematics is probably so different from how do you convince somebody of another thing that they, so I'm not answering very articulately. Michael's going to answer.
One last question.
My proposal to Matea's question is that we actually we computer scientists make ourselves autonomous and build an automated theorem appreciator. So then we can close the loop.
Yeah.
Well, I think another answer is you just make tools that are so much fun to use that people really want to use them.
Well, that is actually what the cartoon is about.
They make fun to use.
Yeah. We're going to have a cup of tea now.
Yeah. Oh, sorry, William's got a question.
Again, I'll ask
Okay.
So let's thank Ursula.